Dear students, आज न्यूमेरिकल प्रॉब्लम्स ऑन थर्मोडायनेमिक्स ਦੇ ਇਸ ਟੌਪਿਕ ਵਿੱਚ ਤੁਹਾਡਾ ਸਵਾਗਤ ਹੈ। ਥਰਮੋਡਾਇਨਾਮਿਕਸ ਦੀਆਂ ਨਿਊਮੈਰੀਕਲ ਪ੍ਰੋਬਲਮਸ ਸੋਲਵ ਕਰਨ ਤੋਂ ਪਹਿਲਾਂ ਅਸੀਂ ਥਰਮੋਡਾਇਨਾਮਿਕਸ ਦੇ ਕੁਝ ਬੇਸਿਕ ਫੈਕਟਸ ਐਂਡ ਇਕੁਏਸ਼ਨਸ ਰਿਵਾਈਜ਼ ਕਰ ਲੈਂਦੇ ਹਾਂ। ਇਸ ਨਾਲ ਸਾਨੂੰ ਪ੍ਰੋਬਲਮਸ ਸੋਲਵ ਕਰਨ ਵਿੱਚ ਹੈਲਪ ਮਿਲੇਗੀ। ਚਲੋ 0th law of thermodynamics ਨਾਲ start करते हैं। This law states that if two systems A and B are in thermal equilibrium with a third system C, then the systems A and B are also in thermal equilibrium with each other. Then the first law of thermodynamics is nothing but a restatement of the law of conservation of energy as applied to heat energy, including internal energy of system. According to this law of thermodynamics, when some quantity of heat dq is supplied to a system, a part of it may increase internal energy of the system by an amount du, while the remaining part may be used up as the external work done by the system dw. It means the quantity of heat absorbed by the system dq is equal to the sum of du and dw during expansion, or dq is equal to sum of du and P into dV. The signs of dq, du and dw are known by some particular sign conventions. These sign conventions are: work done by a system is taken as positive, while work on the system is taken as negative. Heat gained or added by a system is taken as positive, while the heat lost or extracted by the system is taken as negative. The increase in internal energy of a system is taken as positive, while the decrease in internal energy is taken as negative. The relation between pressure, volume and temperature for a system is called the equation of state. For 1 mole of an ideal gas, the equation of state is PV is equal to RT. Thus, for a simple system, maybe for an ideal gas contained in a cylinder, if any 2 of the 3 variables are known, the third one can be calculated using the equation of state. Let me remind you of the internal energy of a gas. A gas possesses intermolecular potential energy. If the volume of the gas increases, work will be performed by the gas against the intermolecular attraction, and hence the potential energy of the gas will increase. On the other hand, to compress a gas, work has to be done on the gas against the intermolecular forces, and hence the potential energy of the gas will decrease. Therefore, intermolecular potential energy of a real gas is function of its volume. The molecules of a gas are always in random motion, and according to the kinetic theory of gases, the average kinetic energy of the gas molecule is given by half into mv square equal to 3 by 2 into k into T, where k is the Boltzmann constant. As the temperature increases, the average kinetic energy of the molecule also increases. A graphical representation of the state of a system with the help of two thermodynamic variables is called indicator diagram of the system. Usually, the thermodynamic variables are taken to be P and V. Thus, the graph between P and V is called PV diagram. Let me show you these PV diagrams for a system undergoing expansion and then for a system undergoing compression. It is mathematically proven that the work done by a system or on the system is numerically equal to the area under the PV diagram. Hence, the PV diagram has an important mathematical utility. Now, suppose that at any instant during the expansion, the pressure and volume of the gas are P and V respectively, then the work done during expansion is given by W equal to integration of P into dV ranging from V1 to V2, provided V1 and V2 are the volumes of the gas during the initial state and the final state respectively. Then, let me also talk of the two specific heats of a gas. Specific heat of a gas at constant volume is defined as the amount of heat required to raise the temperature of 1 gram of a gas through 1 degree Celsius at constant volume. It is denoted by small cv. Molar specific heat at constant volume is defined as the amount of heat required to raise the temperature of 1 mole of a gas through 1 degree Celsius at constant volume. It is denoted by capital CV. If m is the molecular weight of the gas, then capital CV is equal to m into small cv. Also, specific heat of a gas at constant pressure is defined as the amount of heat required to raise the temperature of 1 gram of a gas through 1 degree Celsius at constant pressure. It is denoted by small cp. And molar specific heat of a gas at constant pressure is defined as the amount of heat required to raise the temperature of 1 mole of a gas through 1 degree Celsius at constant pressure. It is denoted by capital Cp. I hope it is clear that capital Cp is equal to m into small cp. The ratio of the two specific heats is denoted by gamma. The relation between two specific heats of a gas can also be calculated by applying first law of thermodynamics, which turns up to be Cp equal to Cv plus R, where R is obviously a constant. And now, let me show and remind you of some thermodynamic processes. In an isothermal process, temperature remains constant. For a system of ideal gas whose internal energy U depends only on temperature, the internal energy will remain constant. In other words, du would be 0. Then, according to the first law of thermodynamics, dq would be equal to P dV. This expression implies that heat supplied in an isothermal process is used to do work against the external surroundings. On the other hand, in an adiabatic process, no heat energy enters or leaves the system. The heat energy remains constant. In other words, dq would be 0. Then, according to the first law of thermodynamics, du would be equal to minus p dv. This expression implies that when a gas expands adiabatically, the internal energy of the system would decrease and the gas will be cooled. The reverse is also true. In an isochoric process, volume of the system remains constant. Or, in other words, P dV would be 0. Then, according to the first law of thermodynamics, dq would be equal to du. That is, if heat is absorbed by a system at constant volume, its internal energy increases by the same amount and vice versa. In an isobaric process, pressure of the system remains constant when heat energy is supplied to the system. So, according to the first law of thermodynamics, dq would be equal to du plus p dv. That is, if heat is absorbed by a system at constant pressure, it is used to do work against the piston as well as to increase the internal energy. Also, during an isothermal change, if P1 and V1 are the initial pressure and volume, and P2 and V2 are the final pressure and volume of the gas, then P1 V1 is equal to P2 V2. Similarly, during an adiabatic change or process, if P1 and V1 are the initial pressure and volume, and P2 and V2 are the final pressure and volume of the gas, then P1 V1 raised to the power gamma is equal to P2 V2 raised to the power gamma. This can be called as equation of an adiabatic change. Finally, the first law of thermodynamics applied to adiabatic process leads us to the equation dq is equal to 0. Since no heat enters or leaves the system, du plus p into dv is equal to 0. And the work done during an adiabatic change for 1 gram of a gas having molecular weight is given by W adiabatic equal to R into T1 minus T2 upon M into gamma minus 1, or it is equal to R into T1 minus T2 upon gamma minus 1, where R is the gas constant for 1 gram of the perfect gas. After having understood and revised the basic concepts and equations related to thermodynamics, you should now be ready to solve some numerical problems. Look at this one to start with. 2 gram of water at 373 Kelvin is converted into steam at the same temperature. The volume of 1 cubic centimeter of water becomes 1671 cubic centimeter on boiling. Calculate change in internal energy of the system. If heat of vaporization is 540 calories per gram. Given that standard atmospheric pressure is 1.013 into 10 raised to the power 5 Newton per square meter. Let's find the solution. Given the standard atmospheric pressure P is equal to 1.013 into 10 raised to the power 5 Newton per meter square. Volume of water is equal to 2 cubic centimeter and volume of steam is equal to 2 into 1671 equal to 3342 cubic centimeter. Therefore, increase in volume dV is equal to 3342 minus 2 equal to 3340 cubic centimeter equal to 3.34 into 10 raised to the power minus 3 cubic meter. If we assume that the expansion occurs at the constant atmospheric pressure, then the external work done dW is equal to PdV equal to 1.013 into 10 raised to the power 5 into 3.34 into 10 raised to the power minus 3 joule, which is equal to 338.34 joule. Now, mass of water M is equal to 2 gram. Latent heat of vaporization for water L is equal to 540 calorie per gram. Therefore, heat absorbed by water dQ is equal to ml is equal to 2 into 540 calorie, which is equal to 1080 into 4.2 joule equal to 4536 joule. According to the first law of thermodynamics, dQ is equal to du plus dW, or du is equal to dQ minus dW. That is equal to 4536 minus 338.34. That turns out to be 4197.66 joule. चलो ਹੁਣ specific heat ਨਾਲ ਵੀ related ਇੱਕ numerical problem solve ਕਰਦੇ ਹਾਂ. The problem is, what amount of heat must be supplied to 0.024 kilogram of oxygen to raise its temperature by 20 degrees Celsius at constant pressure. Given that molecular weight of oxygen is equal to 32, R is equal to 8.3 joule per mole per Kelvin, and Cp for diatomic gases is equal to 3.5 R. Now, the solution. Here, R is equal to 8.3 joule per mole per Kelvin. Mass of the gas M is equal to 0.024 kilogram. Molecular weight of oxygen gas capital M is equal to 32 gram per mole equal to 32 into 10 raised to the power minus 3 kilogram per mole. Hence, the number of moles of the gas mu is equal to small m upon capital M, or mu is equal to 0.024 upon 32 into 10 raised to the power minus 3, which is equal to 0.75 mole. Then the molar specific heat of oxygen at constant pressure Cp is equal to 3.5 R, or is equal to 3.5 into 8.3 joule per mole per Kelvin. So, heat supplied to the gas Q is equal to mu into Cp into delta T, which is equal to 0.75 into 3.5 into 8.3 into 20, which is equal to 435.75 joule. Then look at another problem on specific heat. For air, specific heat at constant pressure is 0.236 calorie per gram per degree Celsius, and specific heat at constant volume is 0.168 calorie per gram per degree Celsius. Density of air is equal to 0.001292 gram per cubic centimeter at NTP. Find the value of J. Now the solution. Here Cp is equal to 0.236 calorie per gram per degree Celsius. Cv is equal to 0.168 calorie per gram per degree Celsius. Density ρ is equal to 0.001292 gram per cubic centimeter. Therefore, volume of 1 gram of air at NTP, V, is 1 upon 0.001292 cubic centimeter. At normal pressure, P is equal to 76 into 13.6 into 980 dyne per square centimeter. At normal temperature, T is equal to 273 Kelvin. Therefore, gas constant for 1 gram of a gas, small r, is equal to PV upon T. On substituting the values of P, V and T in this equation, we get 76 into 13.6 into 980 into 1 upon 273 into 0.001292. That is equal to 2.87 into 10 raised to the power 6 erg per gram per Kelvin. Then, for 1 gram of gas, Cp minus Cv is equal to small r upon J, or J is equal to small r upon Cp minus Cv, that is equal to 2.87 into 10 raised to the power 6 upon 0.236 minus 0.168, which turns out to be 2.87 into 10 raised to the power 6 upon 0.068, or J is equal to 4.22 into 10 raised to the power 7 erg per calorie. And now let's try a problem or two on work done during an adiabatic change. 1 liter of a gas at 125 degrees Celsius and 10 raised to the power 6 dyne per square centimeter pressure expands isothermally until its volume is doubled, and then adiabatically until its volume is redoubled. Find the pressure of the gas given gamma is equal to 1.5. Solution. For isothermal expansion, T1 is equal to 125 plus 273 equal to 398 Kelvin. P is equal to 10 raised to the power 6 dyne per square centimeter. V1 is equal to 1 liter equal to 1000 cubic centimeter. V2 is equal to 2 into V1 is equal to 2000 cubic centimeter. We know that for an isothermal change, P1V1 is equal to P2V2, or P2 is equal to P1V1 upon V2. That is equal to 10 raised to the power 6 into 1000 divided by 2000. That turns out to be 5 into 10 raised to the power 5 dyne per square centimeter. And now consider the adiabatic change. V1 is equal to 2000 cubic centimeter. V2 is equal to 2 into V1 is equal to 4000 cubic centimeter. P1 is equal to 5 into 10 raised to the power 5 dyne per square centimeter, and gamma is equal to 1.5. Equation for an adiabatic change is P1 into V1 raised to the power gamma equal to P2 into V2 raised to the power gamma, or P2 is equal to P1 into V1 upon V2 raised to the power gamma. Therefore, P2 is equal to 5 into 10 raised to the power 5 into 2000 upon 4000 raised to the power 1.5, or P2 is equal to 5 into 10 raised to the power 5 into 0.5 raised to the power 1.5. Taking the log on both sides, we can write log of P2 is equal to log of 5 plus 5 into log of 10 plus 1.5 into log of 0.5, or log of P2 is equal to 0.6990 plus 5.000 plus 1.5 into bar 1.6990. Here, log of 10 is equal to 1. So, log of P2 is equal to 5.6990 plus 1.5 into minus 0.3010, which is equal to 5.6990 minus 0.4515. Therefore, log of P2 is equal to 5.2475. Now, taking the antilog on both sides, P2 is equal to antilog of 5.2475. We have P2 is equal to 1.768 into 10 raised to the power 5 dyne per square centimeter। मैं ਹੁਣ ਇਸ ਆਸ ਨਾਲ ਟੌਪਿਕ ਦਾ ਐਂਡ ਕਰਦੀ ਹਾਂ ਕਿ ਅੱਜ ਪੜਾਇਆ ਗਿਆ ਇਹ ਟੌਪਿਕ ਤੁਹਾਡੇ ਲਈ ਲਾਭਦਾਇਕ ਰਿਹਾ ਹੋਵੇਗਾ। ਟੌਪਿਕ ਤੇ ਧਿਆਨ ਦੇਣ ਲਈ ਸਾਰਿਆਂ ਦਾ ਧੰਨਵਾਦ। ਅਗਲੀ ਕਲਾਸ ਤੱਕ ਆਲ ਦ ਬੈਸਟ।